Alright, so in this lesson we're going to start looking at how do we use those equations from the previous lesson to solve some problems. And the first thing I want to talk about is a little bit of an aside, what I call problem-solving technique. This is the technique for solving problems in physics, and this technique has been developed, at least by myself, through years of study. I've taught or studied physics as a student or a teacher for something in the neighborhood of about 20 years. So I've done a lot of different types of problems, so this type of technique, a way of showing how I'm doing the problem, is very helpful. This technique also follows along with research into what are the best practices for both teaching and learning physics. And I did my graduate research on problem-solving technique and how to manipulate students to do good problem-solving technique. So let's kind of look at what my approach is. And I think of it as a 6-step approach. The first step is obvious, read the problem entirely. The second step is to identify what are the known and unknown pieces of information in the problem. At this point, it might be easy to write that the velocity is 56 meters per second, or the time is 5 seconds, or to draw a picture or a diagram of what's going on. Those are all things that kind of fit under this number 2. The third step, find relationships. Let's really figure out what equations are you going to use in order to solve for unknown values from the things that you already know. The fourth step, do some algebra to solve for the quantity you're attempting to find. You don't just plug numbers in and calculate, you actually do the algebra to solve for the unknown variable first. Now, this is actually a pretty important step, and a step that lots of students miss. And the reason why this is important is it's a lot easier to see what you're doing if you're working with it in terms of variables rather than numbers. My biggest pet peeve is if you come to me and say, I don't know how to do this problem, and I say, well, what have you tried? Punching numbers into my calculator. That tells me you haven't done steps 1, 2, 3, or 4 yet. Fifth step is finally to calculate your answer. This is where you plug in the numbers. And the last step is to check to see if your answer is reasonable. If you get that a person is running at 1,000 meters per second, that's not a reasonable answer. Most of the problems we deal with have answers that are reasonable. So here I have sample problem 2-1, and we're going to take a jogger and he's going to accelerate from rest to 3 meters per second in 2 seconds. And I want to determine the jogger's acceleration and the distance the jogger traveled during this 2-second period. There, I've read the problem. Read the problem. We read the problem. To identify known and unknown quantities. Known quantities, if I start from rest, my initial velocity is 0, and my final velocity is 3 meters per second. The time it took was 2 seconds. So those are the 3 known variables that I have. The 2 unknown variables that I don't know anything about are acceleration and distance. It happens to work out those are the 2 things that I want to calculate in this problem. A lot of times if it's asking you to calculate something that's unknown in the problem. Find relationships. Now there are 2 relationships that I can use to relate initial velocity, final velocity, and time to acceleration and distance. What I call the definition of acceleration equation and the average velocity times time equation are the 2 equations that I would use. My 4th step, do some algebra. Now on the right hand side I'm looking for x, that's already solved for x. On the left hand side I need to solve it for x, or solve it for acceleration. I'm going to subtract the initial, and then I'm going to divide both sides by time. So there we go, I've now done my algebra, solve those equations for the 2 unknown variables. Now I'll do some math, plug in my values and calculate, and I get 1.5 meters per second squared as an acceleration, and 3 meters is a distance. And the question, is it reasonable? Well, these are not unreasonable speeds, 0 and 3 meters per second. It took you 2 seconds to do that. That's a pretty small acceleration. That would seem to be reasonable. 3 meters also would seem to be reasonable. The things to think of if you want to ask, is it reasonable? Are you getting numbers that are about the same size as the numbers that you're calculating? Let's do the second problem. We're going to have a race car that can accelerate from 0 to 50 meters per second over a distance of 100 meters. And we want to know how long does this acceleration take. So there's a picture of what's going on. At time t equals 0, it's traveled 0 meters. At time t equals question mark, it's traveled 100 meters. So if I plug in what I know and what I don't know, I know v initial is 0. I know v final is 50 meters per second. I know 100 meters is x, and I don't know t. So the relationship that I would use is my average velocity times time relationship, x equals v plus v initial over t, or over 2 times t, and I want to solve for t. Looks like I'm going to multiply both sides by 2 and divide both sides by the sum v plus v initial. So if I do that math, there we go, I've done my algebra, solved it for t, plugged it in and got 4 seconds. Is 4 seconds a reasonable amount of time for a race car to accelerate over 100 meters at a football field? I think it is. Is 4 seconds reasonable? Probably. The last problem that I have a car that sits at a stoplight, and when the light turns green, a truck passes the car at a constant velocity of 15 meters per second. The car begins to accelerate at a constant acceleration of 2 meters per second squared. And I want to know how far does the car travel before it catches up with the truck. So there are known values, but there are known values for both the car and the truck. The things that I know about the car is that its initial velocity is 0, and that its acceleration is 2 meters per second squared. There are really 3 unknown variables that I don't know for the car. I have time, distance, but I also don't know final velocity of the car. For the truck, I know initial velocity and final velocity are 15, and I know acceleration is 0. A constant velocity means 0 acceleration. I also don't know time and distance for the truck. Now, when we start to begin to try to plug in some equations, what I'm going to notice is I don't have enough information to simply substitute into an equation and solve for something. I've got to do something a little more sophisticated here. I've got to figure out, is there some shared variable that I could maybe solve each one of these for and substitute one into the other to get rid of that shared variable? Basically set up a system of equations, 2 equations, one that models the motion of the car. If you have 2 unknowns and 2 equations, you can solve for both the unknowns. In this case, I have 2 unknowns. Let's look at my 2 equations. Both of them I could use x equals v0t plus 1/2 at squared as a model. For the car, v0 is 0, so x is going to be equal to 1/2 at squared. The truck, x is equal to v0t because acceleration is 0. Here I now have a system of equations, one that models the motion of the car, x equals 1/2 at squared, and one that models the motion of the truck, x equals v0t, that have the same unknown, distance traveled and time traveled. Now, we can probably agree that when the car catches up to the truck, they had to have traveled the same distance over the same amount of time. If the car catches up to the truck, they have to be in the same location at the same time. That's the definition of catching up. Let's do some substitutes, or let's try to solve this system of equations out. Probably the easiest way to do this is solve one of them for t and substitute in for t because it's easier. Over v0. But again, that and substitute it unknown equals 1/2 times the acceleration of the car times x squared divided by, or times x squared divided by the velocity of the truck squared. Now that's the equation that I can solve for x. And let's solve it out. Let's distribute the square. I'm going to divide everything by an x to get rid of one of the x's. That's going to end up with 1/2 a times x over initial velocity squared. Looks like probably I'm going to multiply by 2 and v0 squared and divide by a. And so there we go. I now have a solution to this problem. That if I take 2 times the initial velocity of the truck and square it, divide by the acceleration of the car, I get the distance these 2 things have traveled. If we plug those numbers in, I get 15 meters, and 15 meters, sure enough, seems like a pretty reasonable answer to me. So that's kind of a quick overview of how to do one-dimensional kinematics problems. I threw one that's a shared variable system of equations problem. You can do all sorts of different types of problems using this technique with this set of 5 equations.